Okay, so I thought I'd try and think of a way to demonstrate the LCR resonance. And to do that, I was wanting an inductor that would work nicely in the audio region. And it just turns out that the isolation transformers work perfectly for this. So I initially used one of these excellent little peak LCR bridges to measure the inductance and series resistance of this device, and it comes out to be about 2.8 henries of inductance and 98 ohms of series resistance. Now, I originally tried to use just one of these devices so that the audio would be coupled in through the other windings of the transformer, but I couldn't make this work. So in the end, I'm feeding the audio as before from the PC through one of these transformers, and I'm using the other one connected only on one side to function as an inductor. So to start with, I thought I'd give a go to the series case. So on the diagram there, L1 and C1 are the inductor and series capacitor. R2 is just the series resistance, and I've chosen a bigger resistance R1 that will dominate, so we can essentially forget that R2 exists for this purpose. The only thing it will have an impact on is the Q factor of the resonance, the width of the plot. So the series case, I guess we can have a look at. So we'll feed it with some audio signal from the laptop here. Feed the audio into there, and what should happen is that as you approach towards resonance, the impedance of the inductor, forgetting about R2, the impedance of the inductor will be the same as the impedance of the capacitor. The same current will be flowing through the both of them because they're series connected, but the voltage across this one will be 180 degrees out of phase with this one, and so because at resonance the reactances are equal, there will be 0 volts across here, and this essentially will be pulled to ground at resonance, so you will find a graph that would generally dip at resonance and then rise at the other side, which will look something like this. And I used this package called QUCS-S, a circuit simulator, to give me an idea of the values that would work nicely with our inductor, and about a 22 nanofarad capacitor works well with this. So I've built up the circuit on the breadboard. If I zoom in a little bit, you'll see the inductor feeds in with the capacitor in series with it as per the diagram, and so we can see how that performs. So what we're going to do, we're going to drive it with a chirp signal. If I can find a tool, here we are. We'll do with a chirp signal which sweeps over 10 seconds from about 30 Hertz to about 3 kilohertz logarithmically. And so we can then look at the scope and see what's happening. So you can see as the frequency increases, the amplitude drops to a minimum at resonance and then rises as you go beyond that. This will just repeat, so you can see again your frequency is going up. As you approach resonance, it dips and then rises at the other side. So let's stop that and rearrange and look at the parallel case. So in this case, we want to rewire this circuit so that the capacitor is in parallel with the inductor, like that. So that corresponds to this case where you've got a capacitor in parallel with the inductor, and in this case you've got the same voltage across each because they're both connected at each end, and instead the current splits a certain percentage that way, a certain percentage that way, again ignoring R2, that at resonance the reactance of each is equal, so the current is split equally but 180 degrees out of phase with each other. So you would essentially at resonance have 0 current flowing through this combined network, and so the voltage at this point will rise up to the supply rail, and And so you should, instead of seeing a dip, you should see a peak up to the supply rail voltage at resonance, which should look like this for the values I've chosen. Okay, so if we test this circuit out, we can plug it in. So now we have the inductor in parallel with the capacitor, and so we should see it peak as it passes through the resonance. So we start to increase the frequency, you can see it rising up to a peak, and then as it passes through resonance it begins to decay once again, and so it repeats, rising up to resonance and then collapsing down again. Now I'm showing this on the oscilloscope. It will of course be possible to read this on the Arduino, so we can plot this graph out, essentially plotting out these curves, but I haven't had the time to modify the software for that as yet. We can demonstrate that later on. Alright, thank you.